So the topic tonight is actually about the utility industry in general, and you know, the issues that they have, and the drivers that are kind of convincing a lot of companies and entities and jurisdictions out there to heavily invest in a smart grid. Just prior to the meeting, we were chatting with some of the attendees here, and the issue came up that the fact of the matter is that investments in a smart grid requires a huge amount of investment, and yet looking at the industry today and realizing the fact that the majority of them are cash strapped, and yet they are talking about that investment kind of shows the necessity of this. We'll be talking about microgrid as a constituent component of a smart grid and the topology associated with that. And we'll then see how microgrid would help the evolutionary path of a smart grid. And we'll then look at the work that we've done at BCIT in collaboration with BC Hydro and a host of other companies who are players in this industry. And also, then I'll be kind of zeroing in on the building blocks of what we've done at BCIT and the functions that each and every block has, and some of the applications that we've envisaged for those components, and then a brief overview of where this industry is going. So problems that of course, you know, the majority of utilities out there are facing, and that varies across the board. But you know, for the last 30 years, I've been working with the utility industry. I've been to a lot of utilities in Asia, in North America, and the funny thing is that the nature of issues are almost the same. The level of sophistication of assets may be different, but the issues are almost the same. And that is, you know, the cost of energy is actually going up, and of course the infrastructure are pretty old. Some of the assets that we have in the ground were designed 30 years ago for a maximum of 25 years of active life. So I mean, you know, you see how fragile some of those assets are. And then of course, you know, mass electrification of almost everything that we do today in our lives. And of course, you know, the issue of climate change that used to be, I guess, denied by a lot of people out there, but I guess, you know, evidence is proving otherwise. And now, of course, solutions that the utilities are looking at is knowing the fact that there is huge amount of investments required in modernizing their systems. The question they have is there efficiencies in the system today that we've not taken advantage of? So, you know, optimizing the use of those assets is one way forward. And of course, the other one is, are we going to allow the users to consume as much as they possibly want? Is there a way of kind of putting a priority system in place so that in the event of major issues that we would be able to rationalize the use of energy? And then of course, facilitating IPPs or independent power producers or cogeneration. And of course, using other sources of energy. There are a number of energies out there that could be integrated into our existing systems, including, of course, wind, solar, so on and so forth. The fact of the matter is that the majority of those sources are still not economical compared to fossil fuel. So there is an issue there. So all of this requires modernization of the electricity grid. If you're trying to manage the demand, if you're trying to achieve higher levels of efficiency, if you're trying to kind of integrate other sources of energy into the existing grid, this grid as we have today the topology and the assets, the way the architecture is put together is not going to work. If you're trying to facilitate cogeneration, for example, if you're trying to allow the end user to feed energy back into the system, you have to have a different system. So some of those, in fact, functionalities could not be realized without having certain changes in the system today. So the existing grid today is basically hierarchical in nature, is centralized. Of course, it's quite inefficient. Only a very small percentage of fuel is, and I'm talking about fossil fuel, is converted into electricity. Of course, the waste heat is not harnessed. And due to the fact that the majority of these power plants are placed, rightly so, away from urban centers and load centers, that we need to go through certain transmission systems, and that of course means loss. And of course, a large amount of generation is reserved to take care of maximum loads. That is not the case always in the system. And of course, domino effect failure. One thing happens right at the bottom of the chain is going to bring down a lot of, in fact, components of the higher layers in response. So, what is a microgrid? When we look at the system that we have today, the question arises: is there a possibility of carving out part of this system and try and modernize some of those functionalities, introduce higher level of intelligence into the system in a highly controlled environment, so that issues that could possibly arise from introduction of new technologies into a fragile grid could be avoided? And that is the basic, in fact, driver for designing microgrids. Microgrids are primarily defined as distribution systems that will have their own local power plants, either wind, solar, geo, biomass, so on and so forth. And normally there is a level of storage associated with these power plants, due to the fact that some of the power plants that are used within these systems are intermittent in nature. Solar, sun is not always there, wind is not always blowing, so you need to have a storage system that would allow you to kind of store the energy and then use it later on. And then, of course, a wide variety of loads, and those loads need to kind of replicate the reality of the utility loads, industrial loads, residential loads, commercial loads, so on and so forth. And of course, the energy flow between the two. And last but not least, which is what defines microgrids, is an energy management system, is that intelligence layer that sits on top of these, in fact, assets and allows rationalization of energy. So if we look at the future grid, and I can't really project in any number of years, but future, whenever that future is going to be, the understanding is that we are going to have a large number of loosely integrated smart microgrids that form what we call the supergrid. And the beauty of this microgrid is that because of the fact that a lot of generation is done locally, you would be able to harness that waste heat in terms of district heating systems, so on and so forth. So CHP, combined heat and power, is a major characteristic of microgrids. At the same time, it allows demand response. You know how much your load is, and that gives you the possibility of generating per requirement rather than generating blindly. And of course, since the generation and of course loads are in close proximity, you don't need to go through expensive transmission systems. And of course, you're able to integrate renewables. And the beauty of microgrids, again, is that anything that goes wrong is going to be confined to the microgrid itself, to that particular microgrid. It's not going to bring down the entire system. And of course, most important of all, which really is the defining characteristic of microgrid, is that it empowers the consumers to have a say in what is generated, how it is generated, and how it is consumed. Unlike the situation today, we are basically sitting at the end of basically a big pipe, and we are basically consumers. We have very little say in how that energy is consumed. But the microgrid is going to ensure that everybody within that proximity that has anything to do with the production of energy, with the consumption of the energy, distribution of energy, has a say in how that is done. Now, the issue is looking at where we are, looking at the fact that a huge amount of investment has already been done in the system. Are we in a position to overhaul the grid, the existing grid, overnight? That's not possible. That's not practical. That's not realistic. Fact of the matter is that the electricity system is a highly critical infrastructure for the economy and day-to-day life of any, in fact, society. And you don't want to introduce unknowns into the system that would jeopardize the reliability of the system. So the projections that a lot of pundits have in the industry is that we are going to have a transition system that will allow microgrids to coexist with the existing grid and gradually transfer loads from the existing grid onto these new highly intelligent and smart microgrids, so that over time these two in fact system would merge in such a way that you would have a huge supergrid. So those are the generalities. 5-6 years ago, when I first started my work at BCIT, we looked at the possibility of, is there a place within the lower mainland where we could actually set up a microgrid? And of course, there were a large number of good candidates. We stumbled upon BCIT's Burnaby Campus, and we thought this is the best place to set up a microgrid, because in actual effect is the worst possible place to set up a microgrid, because of the fact that the infrastructure is crumbling. It's very easy to walk into a newly built area and put all kinds of interesting technologies and smartness into the system. That is easy to do. But if you have an environment in which life is ongoing, operational issues are ongoing, you have students coming in and going, classes are held, and you're trying to gradually introduce functionalities into that environment without disrupting the actual work, and yet achieve those levels of efficiencies, this is the best place to do. So as you see, these are kind of, I'm told, I mean, I'm not old enough to know the purpose of those aircraft hangars, but I was told that these were used during the Second World War for some repairs of the Air Force at the time. The funny thing is that the distribution system in this campus is so bad that whenever we wanted to put anything into the ground, we had to go and talk to our facilities and ask for drawings and plans, and in the process they would find all kinds of underground manholes and tunnels that nobody apparently knew exist at the time. So just imagine the kind of issues that you have in trying to introduce a new system into this place. So the Burnaby campus is interesting in the sense that it actually it was created out of the amalgamation of two different institutes. So because of that, there were two different distribution systems in place. There are 3 different feeders from BC Hydro that feeds the place. And in addition to that, it has a wide variety of different loads. Now, We started with, we got a grant from the government of Canada and ICE fund from the province, and started kind of working on putting the skeleton of the assets in place, in terms of controls and communication systems and relays and servers, so on and so forth. And the issue was, how do we build understanding on how systems could be provisioned into an environment of this nature. Number two was that, how do we do, assuming that these systems are in place, how do we integrate them, work them together, and make sure that they are resilient to kind of problems that one may have. And then, of course, how do we now analyze those issues and model them and understand why they're there. So phase one ran from 2008 to 2010, and I'm glad to report that we've done almost all of this, despite huge challenges of working with our facilities. And I'm sure facilities department in all the lower mainland academic institutions feel the same. I mean, they like any utility, their interest is to keep the lights on. Just don't bother me. Don't be a nuisance. Don't come and play around with my stuff because I have a campus to run. And just imagine, I remember that the very first wave of smart meters that we installed on the campus took our facilities 8 months to approve. And it was amazing. I mean, everything was there. Drawings were there. We had full documentations to back up that we were not doing anything funny, and yet, anyway. So we've got a number of load control devices in our domes. We've got a communication system that is a combination of Zigbee and WiMAX on the system. We've got wind turbines, PVs. We've got cogen on the campus, and we are now kind of retrofitting one of our substations. Second phase was that we managed, with having this assets in place, we talked to Ancillary, and we kind of convinced them that, look, in Canada we have the very first functioning smart microgrid. Why don't we make this available to all the universities from across Canada, to researchers, and enable them to use this facility for their experimentation, development of technology, so on and so forth. Ancillary agreed with that approach. So we were able to get the first grant to set up a strategic research network in Smart Microgrid, of which SFU is a member, UBC is a member, and we've got membership from back east, from University of New Brunswick, McGill University, Toronto, Manitoba, Alberta, all the way to SFU and UBC and BCIT. So that network has already been running for the past 2 years. We just entered our third year. It's a 5-year research network, and they are doing a lot of very interesting stuff. And the beauty of that network is that the money the investments comes from utilities from across the country. BC Hydro, Manitoba Hydro, New Brunswick Power, Hydro One, Hydro Quebec, all are members of this network. And phase 3, which is a placeholder for me, we've not done anything about that, is how do we commercialize what we have in here. So this is the topology of our microgrid, a number of loads. We've got residences, we've got, of course, classrooms, lots and lots of industrial loads, and now we've got a fleet of EV charging stations on the campus as well that we are integrating with loads. We've got a storage, flywheel, and lithium-ion batteries. We've got turbine, 250 kilowatts, PV modules, and of course wind turbine. And of course we've got a smart grid control center that binds the entire thing. Now, if you look at all of this, you realize that the generation capacity that we have is well less than a megawatt, whereas the campus load is around 6 megawatts. So we are not yet in a position to completely take our campus off the grid. However, having said that, the question is, are there times in which the campus load equates what we can generate? And the answer to that is yes. There are certain times that could be done. Now, thermal cogen is basically an intelligent combustion system that could use a wide variety of different fuels. It is a CHP configuration. We've got flywheel 75 kilowatt and lithium-ion storage pack 75 kilowatts that are going. These last two items are not yet put in place, but they are being planned at this point in time. So this is a brand new, beautiful work of art that is installed in one of our facilities, which generates, which is fully functional now. We're just talking about with one of our guests here, talking about the fact that interconnection with BC Hydro grid is a major issue, and although this thing is working and fully functional, it's taken us a few months to negotiate an agreement with BC Hydro in order to activate this, so that we could actually put the energy back into BC Hydro grid. We've got a large number of PVs that are almost everywhere on the campus, everywhere that you have different generation of PVs are put in place. And these PVs, in fact, basically connect up with the grid locally. This is the latest, in fact, array of almost 17 kilowatts that we've put on top of a newly built building on Willingdon. Where, as you're going south on Willingdon, the new building is on your left. It's called Gateway Building, and on top of that building, these arrays, latest generation of PV modules are installed, and they are connected to the grid. We've got a wind turbine, which is a very interesting technology. It's actually built in Saskatchewan. It's a company, it's a Canadian company that is vertical access. It's actually designed for low wind, in fact, speeds, so that these are perfect for urban settings. You could generate a good amount of, say, 4 to 4.5 kilowatts in nearly windy conditions. Again, these are in fact purchased with funding from BC Hydro. It's already been installed and is next to a home, a single-family home that we call Afresh. Is on the campus, and I'll talk about this. This home later on. So, of course, the purpose of this wind turbine is not really generation of power as such, but more how do we integrate, an intermittent source of this nature with the campus grid. So it's got more of a research value than operational value, and that's a very important distinction to make. The beauty of this wind turbine is that it is designed with a kind of a hydraulic arm that allows the turbine to be lowered as required, and we are planning to also use it for educational purposes, training technicians or engineers who hopefully want to know exactly how can one install small little turbines of this nature. This is the kind of turbine that you may see in the near future for a lot of off-grid communities in Canada as the source of their power. Now, We've also, this is the Afresh home, as we call it. Is a single family home that has been built with funding from BC Hydro on the campus. Is a typical North American single family home. I mean, it's got all the characteristics of a single family home, and it was built with the purpose of loading it with a lot of gadgets, with a lot of technology, with a lot of stuff, so that you could see how these different technologies could work together and make and enable this home to be net zero, meaning that it should not really draw any power from the grid. So, for example, within this home, we've got smart appliances. And we've designed a system. There are a lot of stuff that I've not put any slides in here, but a technology that we developed that was really beautiful, and it was demonstrated quite a while ago, was pricing signals. Assuming that in a home you have intelligent appliances, smart appliances, and assuming that these appliances are capable of receiving pricing signals from the grid and then adjust accordingly. So we designed a system that allowed us to send pricing signals from one of our labs on the campus through a substation onto the home. And we put a GE smart meter on the side of the home, and this meter would then receive the pricing signals. The meter had two radios built into it, a 900 megahertz radio and a Zigbee radio. It would take that pricing signal from the substation and then put it on a HAN, home area network, so that all the appliances within home would be able to receive those pricing signals. And then we could program, the dishwasher, for example, say, look, this load of dish should be washed at the cost of no more than $2, for example. And then the system would sit there and wait for these pricing signals coming, and then it would trigger the wash cycle. We demonstrated it to a large number of people, and it was. I'm more than certain that it's going to take BC Hydro and other utilities a number of years before systems of this nature could be actually implemented. But we just wanted to show that these are technologies that are available today. If we are not taking advantage of these technologies, it's not because the technologies are not mature, it's because of regulatory issues. So that's the smart home, and this is what I was talking about, a utility EMS sending pricing signals through a broadband network into our substation, BCIT substation, and then through a 900 megahertz radio into the meter. The meter would then transmit these signals through a Zigbee network to inside the home. And at this point in time, we do not have all of these items. We have washing machines, we have dryers, we have dishwashers, we've got a water heater, and we've got a charging station. So these are all basic functions or appliances that one may have in a home of this nature. And we are slowly and gradually adding other functions into the home. These are some of the load control devices that we've designed, and my team was able to kind of design the software and hardware that sit on top of our water heaters. Our residences are primarily electrically powered. We have no gas in our dorms. And that's a major, of course, issue for our facilities. And we designed a system for them that I'll talk about later that controls how these water heaters could be operated using pricing signals, and scheduling algorithms and software has been written. So the core intelligence of the microgrid comes from a lab which we call SGCS, the Smart Grid Control Center, or control system on the campus. And this, again, this is a piece of, in fact, equipment that we repurposed. It was, this was purchased, I think, 10 years ago to help BCIT with cybersecurity stuff, internet-based or internet-related. And we saw a huge amount of MIPS and in fact, processing power available there. We kind of converted that into a smart grid control center. And from this center, we are able to do a lot of stuff. 4 years ago, before BC Hydro started rolling out their own smart meters, we started putting smart meters on the campus. And we made sure that we populated the campus with a wide variety of different technologies. Our purpose was to make sure that we test the validity of a lot of claims that these manufacturers make. And so in a way, we were there to abuse these systems and see whether or not they could withstand hostile intent of that nature. For example, there was a technology, and I'm not going to say where that technology is from, but it's a technology that is based on PLC, is a power line communication technology, and they were claiming that this technology is capable of operating in just about any environment. Now, there is a feeder on BCIT campus that feeds a bunch of welding shops, and we put those systems on that feeder, and we started testing them when more than 120 students are sitting there and having these big, huge welding machines operating, which puts a huge amount of noise into the system, and no surprise. This is the technology didn't work. It failed to work, and it was very clear that it was not actually designed for that level of noise pollution. Of course, fact of the matter was that we needed to develop our own MDMS, metering data management system, that would allow one single software to be able to read all of these different technologies. We had Zigbee meters, we had ISM band meters, we had PLC meters, all of these different meters. And that's very close to what hopefully is going to happen in any given utility as well, because utilities are not going to adopt one single technology. They're going to have different technologies based on their requirements, and this actually took care of that. And we also put a very sophisticated communication system on the campus, a home area network, a local area network that takes care of our substation, and of course a wide area network, a wide variety of. This is the network status as of October 2010. This shows the connectivity and the linkages that we have between different buildings. And I can tell you that currently I can't really put this map on the screen because you can't see the lines. It's congested. I mean, there are all kind of. So this is an aerial view of where our substations are and where the base stations are and how these are connected together. We've got 22 substations on the campus, and the majority of those are unintelligent. There is very little intelligence built into those substations, and we are trying to gradually put intelligent and smart assets into those substations against all odds. And it's very difficult to, of course, convince our facilities to work with us. We've been trying to kind of identify substations that feed loads that are deemed not critical. For example, this substation is a substation that feeds our gym. So, okay, so I mean, if the gym goes down, no problem. As long as there are no classes disrupted, that's okay. So, that's how we manage to convince our facilities. So these are the sub-projects or components of our microgrid, the AMI, various parts of the campus, the cogeneration plants, the EV charging stations, the control center, and of course the substation. Now, these are some of the software. I should mention that when we talk about the smart grid is really the convergence of power system, communication system, and information technology. So that's really the glue that kind of binds these systems together. And the driver for that is the need to make these systems intelligent. So what we do is that we develop a lot of software that sits on top of these systems and enable them to do things that they were otherwise were unable or incapable of doing. So this is a software that allows the user to kind of schedule their loads. If you have a number of loads, you could schedule your load based on the operation of the target space. When you have classes, when you have labs, weekends, you could schedule your loads according to those options. This is the load control through pricing signals, another approach that we implemented. And you saw this through utility portal, through an EMS server, load control devices, and then controlling the loads. Now, about 2 years ago, we tried to to experiment with some of the assets that we have on the ground. And the question was, is there an environment on the campus that would allow us to kind of bring all of these different technologies together and see whether or not the application of those technologies would be able to help us demonstrate to universities' leadership team that there are tangible values associated with investing in this technology. And we thought, okay, let's work with our dorms, residences. We've got a bunch of residences on the campus, 7 dorm building, 4 suites per building, 12 students per suite. Houses are completely electrically powered and identical, and we wanted to focus on demand response. Now, the problem we had was that there was a lot of waste. Fact of the matter is that our students are not paying for the electricity, for the energy they're using. So, come January, February, you walk by our residences, there are probably a feet of snow on the ground and you see all the windows are wide open. Why? Because the rooms are electrically powered. The baseboards are near the window. There's a nice view. The students put their desk next to the window. So that baseboard heater is behind the desk. And there's a small little knob next to the baseboard heater that gets hidden. So students have it normally all the way up, and it gets too hot, they just open the windows. As simple as that. So BCIT gets to pay a huge amount of electricity bill during the winter time because there is no incentive to save. And of course, there are no awareness. So what we did was that we put smart meters in there. We developed a residence portal. And we started kind of, talking to our students. We put info nights and, got them in, enticed them with snacks, and they came and we, kind of discussed with them what the whole purpose of this thing was, and they liked it. I mean, they looked at, what this portal was capable of doing, and they saw that we were giving them a tool with which they could do something about what they were not aware of in the past. I mean, most of these kids come from from homes, and they never know, you know, who pays for the bill. Normally the parents do, and you know, and this thing never crosses their mind that there's something called, you know, a meter there that clicks, you know, when you leave the window open, and you know, so creating that awareness was the first step to do, and we gave them this portal that not only showed them what they were doing, but also what other residences were doing. So creating that sense of competition that, look, is not only you, but there are other people, and you know, given that sense of commitment, you know, you want to be better than your next door neighbor, hopefully, and that was another incentive. And of course, if that didn't work, we of course, you know, provided them with a lot of information about, you know, what a kilowatt hour is equal to. It equals to this. I mean, you know, giving them information that is tangible, that they could equate with something they know, that this amount of energy, for example, equates to this number of laptops to be on all the time. So that kind of information. And then even if that did not work, we put a prize in there that you know, at the end of the 2 weeks, the house that manages to conserve the most will get free pizza and beer, and is a miracle, you know, how far the promise of free beer and pizza would go in in that environment. What happened was that the competition basically allowed these individuals, these students, to reduce their overall consumption by 21%. Of course, you know, we put some rules in place because of the fact that we wanted to make sure that whatever you do does not create inconveniences for the inhabitants. So there was one residence that we disqualified, and you know what these people had done was that they, you know, in the suite they have like 5 fridges. They had unplugged 4 fridges and jammed everything into one single fridge. Or you know, they were using flashlights at night to steady, or they unscrewed the emergency exit lights, all of that kind of stuff. So all of those, that particular residence was disqualified, but you know, the rest was you know, the overall saving of 21% is huge. I mean, you know, looking at I mean, you know, if you scale that up, you know, looking at our province, we had a surge of almost 14% in terms of our overall load. And just imagine if that kind of system could be put in place to help with the reduction of load, it would defer a huge amount of investment that BC Hydro or other utilities across the province have to do. So what was interesting, which this piece is really what is very interesting about this. Before the competition, this was the curve, you know, that kind of shows during a day, you know, when the students wake up, they shower, you know, then they go to classes and then come back at night, all of this. So this was the curve before the competition started. This was the curve after or during the competition, at the end of the competition. And then what we did was that after 2 weeks, we blocked access to our portal, we removed all the load control devices, so on and so forth, and we monitored the consumption. The consumption did not go back up to this level, it stayed at this level, which means that awareness that we created stayed with our students, which is really remarkable. Because, you know, they started having that appreciation for a resource that is finite in nature, and you know, they wanted to do, you know, use whatever that was available to them to try and conserve. So the functionality of the microgrid at this point in time for us is that we are providing, of course, a unique environment for education and training. Not only our own students, but students from across Canada in our network are capable to run experiments. This past few weeks, for example, University of Toronto has developed a modeling technology, and they're remotely logging on to BCIT campus and running that modeling to see whether or not it works. That's the kind of collaboration that we need to have in the country to ensure that we are able to develop this critical sector. It of course help us reduce or optimize the carbon footprint. That is tall order. Fact of the matter is that we are far away from doing that, and simple reality is that in order to do that, you have to have every single stakeholder on the campus on your side, and that's not always the case. Within our campuses, you have a huge number of people who guard their turf, and it's very difficult to get them work together for in fact collaborations of this nature. But we're working, and we keep at it, and hopefully this will happen. Of course, this is what has been the focus of everything that we've done, and that is BC Hydro and other utilities across the country have been able to kind of use our assets to validate some of the technologies that they are targeting to put in place, and that has been remarkable. And of course, we are working on mitigating some of the critical infrastructure risks. For example, there is one project that we've just recently started, and that project came to the fore due to the fact that somebody asked a simple question, and that was, if there are 10,000 electric vehicles next year on the roads in the Lower Mainland, in the downtown core, what's going to happen to BC Hydro's critical assets? And the question is disaster. The answer is disaster. We need to provide to find ways of mitigating the exposure of some of those fragile infrastructure to loads of this nature. So there's a project that we've just started working about that, and of course being a sandbox. Where are we going with this? Of course, there are a lot of applications that microgrids could aid with in terms of simulating and modeling contingencies, distributed generation, and how this alternative source of generation could be incorporated into the mix, and some of the in fact protection and islanding schemes. If you're looking at a microgrid and you're thinking that, okay, I have enough power to run independent of the grid, how do I do that? How do I make sure that this system could run on its own and be able, in fact, to operate without need for incremental power? And of course, issues related to asset management. The fact of the matter is that today, the majority of our substations, I was told the other day that, okay, I shouldn't name the utility, but there is a utility in a major urban center in the country that has less than 10% visibility over their assets. There's 90% of their assets is just there, and they don't know. I mean, something goes wrong, they have to wait for a consumer to pick up the phone, call them, we don't have power. Then they have to roll the truck from substation to substation, look at the substation and see whether or not the protection relays have tripped or not. Just imagine, right? And that's almost universal across North America. And then, of course, demand response and dynamic pricing, and of course, energy markets. So, where are we now? We are down here somewhere. We've just advanced from our AMI, the advanced metering infrastructure, smart grid, hopefully smart grid compliant. And I'm saying that with a grain of salt, because a lot of AMI systems that have been put in operation across North America are not really smart grid compliant. They are dead ends. And you know, the minute you start looking at the next level of functionality, you realize that you have to basically take those assets off and put new assets in. So assuming that those AMIs are smart grid compliant, you know, you're starting basically from demand response, understanding how outages could be detected, how assets could be managed, how customers could be involved in accessing their data, automate your distribution system, and then move to the next level, which is a smart grid that does wonderful amount of stuff, assuming that this infrastructure is in place, which is from substation automation to preventative measures, load management, emission control, so on and so forth. So that brings me to the end of my presentation. I'll be more than happy to answer any questions. But before I do that, we are more than happy if any one of you wants to take a look at the stuff that we have on the campus. I mean, this is we do a lot of demos, and normally a large number of delegations, especially from overseas, actually come and look at our stuff. So, you know, if you're interested, maybe you know you could organize you know a group tour, and we'll be more than happy to host you. Thank you.
What about the software that you're using? Is it like a commercial software off the shelf, or it's mostly designed by BCIT? Because I'm guessing you have all part of programming to be able to decide that I'm talking to the dishwasher, I'm talking to...
Right. So it's a combination of the two. That is, at the moment there are software available that does certain things. But in order to put that software in a system, you need to ensure that it talks the same language, same protocol, and the interfaces are the same, and you're able to kind of manage that functionality. So what we've ended up, as I mentioned, for example, in a case, we have different metering systems on the campus, and each metering system comes with their own MDMS. But now you have to design a different software that sits on top of these different MDMSs and brings all of these different data into a single portal. So that's the kind of software that we've developed.
David Field with Centronics, Energy Systems. Are you considered by BC Hydro to be a commercial entity? In that there's residential, commercial, industrial. The question reflects the power factor. So you explained that you have welding machines, you have all electric heat. So my guess is that you have very poor power factor. So in your topology, what I didn't see was any capacitor banks. So my question is as part of your smart grid, is the plan sometime in the future to introduce capacitor banks in there to correct the power factor so that you're closer to unity?
Yeah, very good question. Actually, you know, one of the projects that we are currently doing within the network is volt-var optimization, and we're taking and our feeders are notorious. I mean, there are feeders that have primarily reactive loads on them, and of course, BC Hydro is charging us for active as well as reactive energy that we're using. But as I said, the project that we are currently doing aims at looking at what kind of volt-var assets can be put, including capacitor banks or voltage regulators, so on and so forth, on the feeder, so that we will be able to, to optimize the voltage, the power factor. At the same time, there is another, in fact, possibility called CVR, conservation voltage reduction. We are also working towards that as well. Again, most of these technologies have been talked about in the industry, but no one is implementing them yet. We are trying to implement those, develop the algorithms, develop the system around it, so that it could be demonstrated to the utilities that these are doable and could be rolled out within the confines of their existing systems.
Yeah, I was at, the reason I brought that up, I was at a conference in Houston, Texas, put on by ETB, Steve Brown-Baveri, and they were premiering a new system called SCC Lite, which is static bar composition light, which again is for large master banks. And that was introduced 2 years ago at the convention. And so I'm just wondering if that might be something that you could use in the future.
Right. Let me be a bit more technical about that. There are two different approaches on that. One is one looks at the network model using the load factors at the network level in order to optimize the system. Our approach is, and by the way, that's what a lot of utilities are doing today. We are taking that and kind of ripping it apart and saying, can't we do optimization at the feeder level? If we had the option of understanding what our load profile is on any given feeder, couldn't we use our local resources, VVO assets, to optimize that feeder?
Arman Bonakdabur from UBC Clean Energy Research Center. I'm wondering if you could elaborate a little bit about the energy storage system that uses the combination of flywheel and lithium-ion battery, how it works, how you do the battery management system, what products you use, what's the lifetime and the reliability of the system.
Right. I mentioned that the lithium-ion batteries and flywheels are planned. As the lithium-ion pack, as I know, is sitting somewhere in a warehouse today on BCIT campus. We've not yet, hooked it up to our system. Flywheel was a major headache because we needed to find a place on the campus, dig the ground, and bury this thing, and it wasn't easy to do that. But flywheel is primarily as far as our system design is concerned, flywheel is going to be there to deal with primarily power quality issues. We are not going to use that for addressing intermittencies of the renewable generation, for example. The lithium-ion batteries are different. I mean, looking at the amount of or the capacity, they're like 75 kilowatts. They're not really big, but again, they are going to be there in order to help us kind of see the issues related to the integration of these assets. Having said that, let me just mention that most of these components actually come with a management system already pre-installed. The lithium-ion batteries come actually from EPRI, and they have their own battery management system. So we just interface to that battery management system.
Didn't BCIT have a system for generating from the waste wood products from the shop? Did that proceed?
I am not aware of that. I know that we talked about that quite a while ago, and the conclusion at the time was that we do not have enough waste on the campus. We have joineries and carpentry on the campus that generates a lot of waste wood. But that is not sufficient to justify having a power plant on the campus. The cost of trucking waste wood from outside of BCIT
is there any other type of biogeneration from?
No, but I know that there's talk about a biocube. I'm not too sure what it is. I'm an electrical engineer, but I've heard that there was some project somewhere that is identified by BioCube. I'll probably learn more about that in the next couple of weeks.
The thermal plastic we're talking about, the new generator, is that natural gas?
Is a multi-fuel, so it could use pellets. It could use, of course, natural gas. And every time you have to program the combustion system to deal with the kind of fuel that you have. At this point in time, we're using natural gas only.
Hi, you addressed you guys are doing a project with BC Hydro for electric vehicles. Just wondering if there's any plans to do any modeling on smart charging with EVSEs.
Yeah, so again, BC Hydro's interest is primarily on what impact would a fleet of charging stations have on any given substation. The project that will be announced in the next 2 or 3 weeks, and I'm not going to talk too much about that, enables us to kind of design the blueprint of the gas stations for Canada's EV charging stations. So the assumption is that in the not too distant future, next to every substation, you'll have assets that would allow EV drivers to pull up to that facility and charge their cars. Indeed, we've had a lot of buy-in from the utilities, but it's very difficult to penetrate the auto market. The car manufacturers do not really are not yet in a position, to kind of entertain the idea of working with a research center for issues of that nature. So we don't have that much of a buy-in from that. All I can say is that there is a company, there's a local company which is an offshoot of a major European car manufacturer that is now signed up to the project that we're doing, and they have, at the moment they have gas vehicles in Vancouver, but they're planning to bring in EVs, and they've signed up to work with us to look at the fleet-wise charging issues related to EVs.
I was wondering, within your grid, if you have been able to, it sounds like you're focusing mostly internally, the interaction between the products. Have you looked at the impact of your grid now, your total load on BC Hydro system, so your peak, for example? And would you go even further to look at, would your system be able to provide regulation service to BC Hydro, that sort of ancillary service?
Sure, and that's definitely the way to go. Issue is, as I mentioned, the total generation capacity that we've been able to put in place is much less than what our peak load is, and much of that generation is also intermittent. So at this point in time, we are not even in a position to entertain the idea of providing regulation service for a big utility. Having said that, there are other issues that we could look at, and that is if within that microgrid we are able to carve out individual or smaller microgrids, and if you were to kind of see how the integration issues between these microgrids, and whether or not one could provide regulation service for the other, or one could aid in terms of understanding the load trajectory for the other. How would that be done? We are not there yet, but that's certainly one of the areas that we should look at.
And part of that, I imagine you could monitor and modulate the loads as well. You wouldn't have to just rely on generation to provide regulation.
Sure, definitely. Yeah. I mean, those I did not show this, but the water heaters that we have in the residences, our team has developed a kind of a cycling algorithm that allows something like 10 to 12% efficiency on top of what we have today, without creating any inconvenience for the residents. So those are the kind of stuff that we do.
Just a quick question. You explained that you had on the new installation of that new building, you put some solar panels on the roof, and you said a high efficiency. maybe this question, I'll have to send you an email and find out. Will you know what the efficiency rating is, percentage?
I'm not too sure, but all I know is that we've paid a lot of money for those with the premise that they are efficient. I'm not too sure.
Hi, Bruce Townsend with Ecotages. You've done some interesting work with your social benchmarking, particularly when that was within the residences.
Right.
So have you done any load disaggregation work as well? Load analysis, data analysis?
Interesting, yeah. So I know that you're interested in that, and you're actually, we're actually working with you guys on a project of this nature. Indeed, that's a project that not my team, but I've been kind of approached through my contacts in the States, through DOE, to put proposals to DOE, the Department of Energy in the U.S. for some work in that nature. And indeed, the issue is, if you have portals that kind of house huge amount of data that we've captured from our termination points, how do we digest that data? How do we identify what loads were active when to generate that kind of a profile? There's a lot of interest down south in the States about this. I've not seen that level of interest up here yet, but maybe back east, not here in BC.
And just sorry, if I may, just a follow-up question on that one. And you guys have got such a fantastic array of different usage types, commercial or industrial and residential. And we were just talking about ancillary services, for example. Have you guys looked at, and I know this isn't an issue in BC in particular, but in other jurisdictions it is, analyzing again the load for demand response opportunities?
Yeah, not to the degree that would allow us to kind of have too much leverage with controlling the loads. As I said, when you are working in a fully functional campus with infrastructure that is fragile, it's very difficult to go that far. I was telling my counterparts the other day that although this was not a competition, when I started working at BCIT, a year after our project was funded and we started working, I got to know that UCSD, University of California, San Diego, they started a similar project. They started with $50 million worth of funding. I started with $5 million of funding. And today, they are at least 2 years ahead of me, in terms of what they've done. I went down there to look at what they've done, and I was amazed, realizing that the reason why they were so far advanced was because the entire project was actually driven by their facilities rather than by their researchers. That's a contrast, because in BCIT, the projects are driven by researchers. But in San Diego, is their facilities. So everything that they put in place has to have a tangible output for the operation of the campus. And because of that, they're able to do much more than what we've been able to do up here.
Mike Schuler, Variable Grid. As you know, we're working on automatic load control for EVSEs. Do the EVSEs that you're using in your test area, do they have any smart grid boards inside them?
No, the one that we're using has a Modbus on it, and yes, it's got a Modbus on it, and we are able to talk to the Modbus. We have a software that talks 61850 and Modbus, and that software talks to these EV charging stations and kind of gives them the trajectory within which they should operate. There's also breakers on those charging stations so that you could take them completely off the circuits. Just if you could wait a couple of weeks, I think this will be announced what kind of charging stations we are going to use. Thank you.